Hi, a very good morning to Doctor and my fellow friends. Today our presentation for assignment 3 is about the topic 9, redox equilibriums. This is our group member. I'm sure it's me, Tan Jun Hong, and also Lali Li. This is the table of contents. It includes 9.1 until 9.6. Okay, now look at the 9.1, oxidations and reduction. Okay, this is the learning standard for 9.1. It includes describe redox reactions, expand redox reactions based on the change in oxidation number, and investigate displacement reactions as a redox reactions. Okay, oxidation and reduction. Okay, what is oxidation? Oxidation is the process of gaining oxygen, losing hydrogen, increase in oxidation number, process of a species oxidize when it lost electrons. Okay, reduction is the process of losing oxygen, gaining hydrogen, decrease in oxidation number, and the process of species is reduced when it gains electrons. Okay, oxidizing agent. Okay, oxidizing agent is a substance that oxidizes another substance. Reducing agent is the substance that reduces another substance. Okay, redox reactions. Okay, redox reactions involves oxidation and reductions that occur simultaneously, involves transfer of electrons and change in oxidation number. Okay, this is the example of oxidations and reduction in terms of loss and gain of oxygen. Okay, look at this. The zinc gain oxygen which undergo oxidation to form zinc oxide, and the lead oxide lose oxygen to form the lead which undergo the reduction. Okay, the zinc is a reducing agent and the lead oxide is an oxidizing agent. Okay, this is the example of oxidation and reduction in terms of loss and gain of hydrogen. Okay, here the ammonia loses hydrogen to form nitrogen which undergo oxidations, and the bromine gain hydrogen to form the hydrogen bromide which undergo the reductions. Okay, the ammonia is a reducing agent and the bromine is an oxidizing agent. Okay, this is the example of oxidation and reduction in terms of electron transfer. Okay, the sodium will lose of electrons and which undergo oxidations to form sodium ion, and the chlorine will gain of 2 electrons which undergo reductions to form the chloride ions. Okay, therefore the sodium will act as reducing agents and the chlorine will act as oxidizing agent. Okay, this is the example of oxidation and reduction in terms of change in oxidation number. Okay, look at here. The magnesium undergo oxidation to form magnesium oxide, which the oxidation number is increased from 0 to positive 2. The copper oxide will undergo reduction to form the copper. Therefore, the oxidation number will decrease from positive 2 to 0. Okay, the magnesium is a reducing agent and the copper oxide is oxidizing agent. Okay, this is the rule of oxidation state for the elements. Okay, for element group 1, group 2, and fluorine, the oxidation state is always like this, and the oxygen, chlorine, and hydrogen is usually like this. Okay, the sum of the oxidation number for neutral compound is equal to 0, and the sum of the oxidation number for monoatomic and polyatomic ion is equal to the ion charge. Okay, the nomenclature of compound is very important in this topic by using the IUPAC system. Okay, according to IUPAC system, the Roman numeral must enclose in bracket and written to the next metal when naming the metal with more than one oxidation number. Okay, nobody look at this example. Okay, for FeSO4, the nomenclature is iron 2 sulfates, and this is because the oxidation number of iron is positive 2. Okay, for FeCl3, okay, the nomenclature is iron 3 chloride. This is because the oxidation number of the ion is +3. Okay. Look at this example. Calculate oxidation number of Nm in KMnO4 and give the nomenclature according to IUPAC system. Okay, this includes the several steps. Okay. Okay, step 1, we write out the charge. For the K is +1 and the oxygen is -2. The step 2, okay, times with how many K? Okay, it has only 1, so times 1, and it has 4 oxygen, so times 4. Okay, the step 3, okay, add up all the elements, okay, to equal to 0. Okay, the step 4, calculate the Mn is equal to +7. Okay, the +7 is equal to the oxidation number of the Nm. Okay, the IUPAC name of the KMnO4 is potassium manganate 7. Okay, why this is 7 in bracket? Because of the oxidation number equal to +7. Okay, look at this diagram. Okay, this is the redox reaction for the change of ion 2 to ion 3 by the bromine water. Okay, the bromine liquid is added to the iron 2 sulfate and the color of the solution is changed from the green to the brown. Okay, this is because the bromine water oxidized iron 2 to iron 3. The presence of iron 3 is confirmed by the brown precipitate form. The iron 2 will lose electron and oxidize to iron 3. Okay, the bromine water will act as oxidizing agents and the iron 2 will act as reducing agent. Okay, look at this. This is the half equation for the oxidation and reduction. Okay, this diagram shows the redox reactions for the change of iron 3 to iron 2 by the zinc. Okay, the solution changes from brown to the green color. Okay, this is because the zinc powder reduced iron 3 to iron 2. Okay, the presence of iron 2 is confirmed by the green precipitate form. Okay, the zinc will lose electron and oxidize to zinc ions, and the iron 3 will accept electron and reduce to iron 2 ions. Therefore, the iron 3 will act as oxidizing agents and the zinc will act as reducing agents. Okay, look at this. This is the half equation for the oxidation and reduction. Okay. This is the electrochemical series. Okay, when going out, the tendency for elements to ionize increase, the electropositive will increase, and the reducing agents will decrease. Okay, when going down here, the ion to receive electron increase, the electropositive will decrease, and the power of oxidizing agents increase. The element that located in the higher electrochemical series can display other elements that are lower from its solutions. Okay, this reaction is called a displacement reaction. Okay. For the displacement of metal from its solution as a redox reaction. Okay, look at this example. This diagram is show the reactions between magnesium and copper 2 sulfate. Okay, the magnesium and the copper sulfate solutions, okay, will form the copper and magnesium sulfate. Okay, this is because magnesium is more electropositive than copper, as magnesium is in the higher electrochemical series. Okay, the magnesium can display copper for its solutions. Okay, now I will go back to the home. Okay, now I will explain 9.2 standard electropotential. Okay, the learning standard for 9.2 is about describe standard electropotential, determining oxidizing agent and reducing agents based on their value of standard electropotential. Okay, standard electropotential enough. Okay, what is enough? Enough is the potential difference recorded as voltage between the two electrodes. Okay, the standard electropotential occurs in the standard conditions. Okay, at temperature 298 Kelvin, pressure 1 atm, and the concentration equals to 1 molar. Okay, this is the table of standard electropotential in aqueous solutions. Okay, this shows the stronger oxidizing agents and this shows the stronger reducing agent. Okay, the more positive value of E naught, the more easy the atom will undergo reductions. And the more negative value of E naught, the more easier the atom undergo oxidations. Okay, look at here. This diagram shows the measurement of E naught using standard hydrogen electrode. Okay, this use the catalytic. Okay, this is the standard hydrogen electrode at 1 atm. Okay, using the standard temperature, voltmeter, strawberry, and the zinc electrodes. Okay, the voltmeter indicates a potential of 0.7 volt. Therefore, the E naught of the cell is equal to 0.7 volt. Okay, the diffraction of voltmeter indicates electrons are moving from the zinc group to hydrogen electron. Okay, this is the half equations. The zinc undergo oxidations and the hydrogen ion will undergo reductions. Okay, we also need to know how to determine the oxidizing agents and reducing agent in the displacement reactions. Okay, in these questions, is magnesium able to displace silver from a solution of silver nitrate? Determine the oxidizing and reducing agents. Okay, how to solve the question? Okay, they also have several steps. Okay, the step one, we need to determine the electrode potential for each metal. Okay, the E naught we can get it from the table of standard electrode potential. Okay, the E naught, this is negative and this is the positive. Okay, step two, okay, we need to determine which metal will more likely to reduce and which will more likely to be oxidized. Okay, silver has positive E naught, magnesium has negative E naught. Therefore, silver is more easily reduced and magnesium is more easily oxidized. Okay, the silver ion will undergo reductions and magnesium will undergo oxidation. Okay, next. The last step, we need to write the redox reactions. Okay, look at this. Okay, we need to write the reduction and oxidation half reactions. Okay, so we can know that the silver ion is the oxidizing agents and the magnesium is the reducing agents. Okay, therefore it can be concluded that magnesium will be displaced silver from the silver nitrate solutions. Okay, I think that's all for me. Now I will pass to my partner. Thank you very much.
Hello guys, today I would like to continue the presentation of the 9.3 which is voltaic cell. In this terminal card we learn how to explain, the student are able to explain the redox reaction in a voltaic cell. For next slide, we discuss first what is the cell potential. As first we have learned about the electrode standard potential. Next, the cell potential is the potential difference between two half cells in an electrochemical cell. And here, the electrochemical cell here exhibit the redox reaction, which is the oxidation that occurs at the anode, and the reduction will occur at the cathode. And for the next, the formula for the E naught cell. What is the formula for the E naught cell? The E naught cell equal to the E naught reduction plus with the E naught oxidation. That means the E naught cell is the standard cell potential under 1 mole atm, 1 atm, and also 298 Kelvin. For the E naught reduction is the standard reduction potential for the reduction half reaction occurring at the cathode. For E naught oxidation is the standard reduction potential for the oxidation half reaction that occurring at the anode. Okay, for the next slide, after we understand what the reaction happening in the voltaic cell, let we see an example. The real reaction in a voltaic cell. The diagram shows the voltaic cell. Hence, the label already the anode as the copper as anode and the silver as a cathode. At the copper, at the anode, the oxidation will occur. Hence, the Cu will release the electron to form the Cu2 plus. Then the E naught oxidation is negative 0.34 volt. Hence, and the other side, which is the silver, is undergo the reduction. The Ag plus will receive the electron to form the Ag solid, which is the E naught reduction is equal to 0.8 volt. Hence, after we get the half cell equation of half cell, we need to balance it and we need to sum it together and also simplify it together. And next, we need to calculate what is the potential of the half cell reaction. For the potential is the E naught cell equal to the E naught reduction plus with the E naught oxidation, hence is 0.8 volt plus with the negative 0.34 volt and equal to 0.46 volt. And next, here is the discussion about redox reaction in a volatile cell. And then we go to our homepage to learn about another topic, which is electrolytic cell. What is electrolytic cell? Electrolytic cell, we have to learn about we need to learning what is the electrolysis. Then we need to learn the electrolysis of the molten compound through the activities. And next, we need to explain the factor that affect electrolysis of aqueous solution. Then we will compare the volatile cell and also the electrolytic cells. And the last part is electroplating, also the purification of matter by the electrolysis. Here we go. First, why electrolysis? Electrolysis is a process, a compound which is separated into the constitutional element when the electric current passes through an electrode. In electrode, the energy will change from electric energy to chemical energy. Next slide. Okay, here we go. What is the component in electrolysis? The electrolysis has three components. Main component is electrolyte. It's a compound of in molten form or aqueous solution which conduct electrical. For example, is the NaCl solution. And next, in the solution, it contains the charged ion. The charged ion is moved freely in the electrolyte. The charged ion with the positive charge is the cation, and with the negative charge is the anion. And the ion will attach to the electrode. The electrode is a conductor which is immersed in the electrolyte and connected to electric source. The anode is a electrode that connected to the positive terminal, and the cathode is the electrode that connected to the negative terminal. Okay, can you watch me? Here we go for the next slide. Okay, here this is an example of the electrolysis of molten ionic compound. First, how we can explain this electrolysis? First, I will need to do is identify the cathode and anode first, and next we need to identify what the ion will present in the cathode and also anode. Next, we need to observe what will happening at the cathode and what will happening at anode. We need to do the observation, and next we need to write down what is the half equation at cathode and also the anode. And then the last part is we need to balance the overall equation. How we do balance is we need to use the half equation to balance it. And for the next slide is here is the discussion for the electrolysis of the molten bromide. At cathode, the negative terminal, the positive ion will attach, and they will undergo the reduction to receive the electron to form a Pb solid. Hence, a soluble deposit at the limiter of this electrolysis. At the anode, which positive terminal, the bromide as a negative ion will attach to the positive terminal. Hence, the brown film in the bromide gas are seen in the anode. The bromide will release the electron to form a Br2 gas, the bromine gas. Hence, we can observe the brown film of bromine gas. Hence, after that, we need to add the half equation together, and we need to summarize, simplify, and do the overall equation. And next slide is what the factor will affecting the electrolysis of aqueous solution. First is the position in the electrochemical of series. Next, the another one is the concentration of the electrode, and the third one is the type of the electrode. And next, we will do a further discussion to compare what is the difference between the voltaic cell and also the electrolytic cell. Here is diagram. We can see the diagram as my left hand side is the voltaic cell, and my right hand side is the electrolytic cell. For the next, here, what is the difference between here is the voltaic cell is convert the chemical energy to the electrical energy, and the electrolytic cell is convert the electrical energy into the chemical energy. For the voltaic cell, the reaction is spontaneously, and the electrolytic cell is the reaction is induced from the external electrical energy source. Hence, it requires the external voltage source. Hence, at the anode in the voltaic cell, the anode is a negative electron and cathode is a positive electron. Hence, but at the electrolytic cell, the anode is a positive electron and the cathode is the negative electron. For the voltaic cell, that does not require any external voltage source. The electrolytic cell is required an external voltage source. Let me see what is similar between the voltaic cell and also the electrolytic cell. First is the reaction at the anode and also the cathode. The oxidation will occur at the anode and also the reduction will occur at the cathode. This is a similar, exactly same. And next one is the flow of the electron. The electron will flow from anode to the cathode. This is exactly same in the voltaic cell and also the electrolytic cell. And next, we want to discuss about what is the electroplating. In the electroplating, we need to do is, here is the diagram for electroplating of the silver spoon. First, the electroplating is a process that uses the electrolytic current to reduce dissolved metal ion by using the electrolysis to obtain the dissolved metal ion at the another electrode. First, we need to identify first what is the cathode because they undergo the reduction. First, the spoon will act as the undergo the reduction because Ag will receive the electron to form the Ag solid. So the spoon will be plated. And next, to identify the anode, which is what compound? The anode is a Ag plane at the Ag, the silver, hence they will act as a spherical anode or inert anode or an inert anode. Hence the Ag will release the electron to form the Ag plus, and the release the electron, hence the cathode can accept the electron from here. And next, the electron will transfer from anode to the cathode. Hence, this is underway in the solution containing the silver. So the solution we use here is the AgNO3, which is the silver nitrate. And for next slide is we need to discuss about the purification of metal. What is the purification method? First, what we need to do is we need to identify what is the anode, what is the cathode. In this purification, the anode is impure copper we use, and the cathode is the pure copper we use. Here we identify in the copper in anode, the Cu2 plus ion will go to the solution at the anode. First, the Cu will dissolve first, and the Cu2 plus ion will go to the solution. Hence, the anode copper will become thinner. Hence, the anode reaction in anode is Cu release the electron to undergo oxidation to form the Cu2 plus ion. For the next, at cathode, the copper ion is relatively charged and dispositive. The cathode copper is become thicker. The cathode is the Cu2 plus ion receive the electron to form a Cu ion. And in this experiment, the blue intensity of solution is remain unchanged because the solution used in the electrolyte is the copper sulfate solution. That's all for my presentation. Thank you for listening. See you.
Now I will discuss about the extraction of metal from its ore. At the end of this lesson, you are able to explain the extraction of metal from its ore through electrolysis process, and also explain the metal extraction from its ore through reduction process by carbon. From this table, we can see that the more reactive the metal is, the more difficult it is to extract from its ore. So for the very reactive metals, they are extracted by electrolysis of molten ores. For example, the electrolysis of molten aluminum oxide. Later we will discuss further about this one. Then for zinc, iron, tin, and lead, they are extracted by using carbon in blast furnace. For copper and mercury, they are extracted by heating directly sulfide metals in air. For the less reactive metals, they exist as free metals in the nature. Let's look at the extraction of aluminium. The aluminium ore is called bauxite. The bauxite is purified to white powder, and we always call it as alumina. And this extraction of aluminium can be done by electrolysis. The aluminium trioxide must be melted first so that the electricity can pass through it. The aluminium trioxide is dissolved in molten chloride. This molten chloride is an aluminium compound with lower melting point than aluminium oxide. And this molten chloride acts as a solvent to reduce some of the energy costs. The diagram here shows the simple electrolysis cell for the extraction of aluminium. The negative terminal here acts as cathode, the positive terminal here acts as anode. At the cathode, the aluminium ion is reduced to aluminium. At the anode, the oxide ion is oxidized to oxygen. For the extraction of iron, the raw material involved is hematite. For the process, the iron is extracted from the oxide by reduction using carbon, and these are the chemical equations involved in the extraction of iron. The extraction of iron can be done inside the huge container like this. This container, we call it as blast furnace. Now you know about the extraction of metal from its ore. So let's continue our lesson to know about rusting. Now I will discuss about the rusting. At the end of this lesson, you are able to describe the metal corrosion process as redox reaction through activities and also describe the experiment to prevent rusting. The rusting is the corrosion of iron. Rusting is also the redox reaction whereby the oxygen acts as oxidizing agent and iron acts as reducing agent. The rusting of iron can be occur in the presence of oxygen and water. This is the mechanism of rusting. This is iron and this one is the water droplet. And the black area here and here is rust. At the middle of the water droplet, it acts as anode, whereas at the edge of water droplet here and here, it acts as cathode. At the anode, the iron is oxidized to iron 2 ion and the electron is released. At the cathode, the concentration of oxygen is very high. The oxygen and water receive the electron transfer from the anode and then reduce to hydroxide ion. So this is the reaction occur at the anode and cathode. The iron 2 ion formed at the anode will combine with the hydroxide ion formed at the cathode to form iron 2 hydroxide. Then the iron 2 hydroxide is oxidized by oxygen to form iron 3 hydroxide. In this stage, the iron 2 ion is oxidized to iron 3 ion. Then the iron 3 hydroxide is oxidized by oxygen to form brown solid. The brown solid is hydrated iron 3 oxide. And this hydrated iron 3 oxide is also known as rust. These are the ways to speed out rusting. First, we can use the strong electrolyte such as acid and salt. Then, if iron is in contact with a less electropositive metal, the rusting also can be speed out. For example, copper and lead. Let's look at the electrochemical series here. The position of iron is at the middle here. When iron is in contact with the less electropositive metal such as lead and copper, then the iron will be oxidized first, so the rusting is speed up. And these are the ways to control rusting. For the galvanizing process, the material is coated with zinc metal. The galvanizing process is used on materials that are exposed to atmosphere, such as the zinc roofing and also the iron rubbish bin. For sacrificial metal protection, the iron is attached to a more electropositive metal such as magnesium and zinc. When iron is attached to a more electropositive metal, the more electropositive metal will be oxidized first instead of iron. So this method can use to control rusting. Then the electroplating, such as tin plating process, because the tin can provide a protective oxide coating which will prevent the rusting. There are also other ways to control rusting. For example, we can use the pen, we can apply oil and grease to protect the moving part of the motor, engine, or machine. Then the alloying is also one of the methods can be used to control rusting. Alright, this is the experiment to study the effect of other metals on the rusting of iron. And the material that we needed in this experiment are iron nails, magnesium ribbon, copper strip, hexacyanoferrate solution, phenolphthalein, and jelly solution. The apparatus that we needed are test tube and sandpaper. This is the procedure for the experiment. First, we clean the iron nails, magnesium ribbon, and copper strip with sandpaper. Why? Because we have to remove the outside layer of the metal first. Then, the two of the iron nails are coated with copper strip and magnesium ribbon respectively, and then we place it in the different test tube. Next, we take another clean iron nail and then place it in another test tube. Next, the mixture of jelly solution, hexacyanoferrate solution, and phenolphthalein is poured into the test tube. Then the whole set out is left for a day. And this is the apparatus set out for this experiment. Now let's look at the function of the solution. For jelly solution, it is used to see the pink and blue coloration clearly. Then the potassium hexacyanoferrate solution is used to detect the presence of iron 2 ion by blue coloration. So if the rusting is occur, then we can see the blue coloration form. Next, the phenolphthalein is used to detect the presence of hydroxide ion by pink coloration. When iron is in contact with magnesium, the rusting is prevented. Why? Because magnesium is more electropositive than iron. So the magnesium will be oxidized first. The magnesium will be oxidized to magnesium ion. So the rusting is prevented. However, when iron is in contact with copper, the rusting is occur. And we can see the blue coloration form. Why? Because the iron 2 ion is detected. Because the iron is more electropositive than copper, so the iron is oxidized to iron 2 ion, and the rusting is occur. The conclusion that we can make from this experiment is the rusting will be faster when iron is in contact with a less electropositive metal. However, the rusting can be prevented when iron is in contact with a more electropositive metals. Alright, that's all for our group today. Thank you very much.